Franco Molteni is going to provide a kind of theoretical lecture on data on comparing ERA 5 data with seasonal forecast data and bias correction. So Franco, I'll hand over to you.
Yeah, thanks, Chris. Let's see whether things are working. Can you see this presentation?
Yes, we can see it. If it's possible to put it into presentation mode.
Should be presentation mode now.
Maybe give it a bit of. Yes, perfect. Great. Thanks a lot.
Okay, thank you so much. Thanks to the organizers for inviting me to present this application, which has been developed by the Italia Meteo Agency, which is basically the civil Italian meteorological service, as a part of an EU-funded project called Albatros, which is concerned with creating climate services for Africa. So the work that I'm going to present has been done in collaboration with my colleague Daniel Pavone at Agenzia Italia Meteo. And basically, what I'm going to present is an application of how you can use a specific type of statistical downscaling, which is quantile mapping, to calibrate and downscale seasonal forecasts that are available from C3S. And this is just basically a demonstration tool for the moment. So we only use the data from the ECMWF system, and we have used the ERA 5 and ERA 5 land data to develop the system. Now, a bit of motivation. As the previous speakers have said, we have to refer seasonal forecast data to the climatology of the model which is producing this data, because each model has its own climatology, but more complicated than that, since we are actually initializing all these models with real data. They basically start from the observed climatology, and then they drift gradually during the course of integration towards their own climatology. So if you take a variable, let's say with a 3-month lead, for example, then you will have to compare the raw data with the model climatology at the same time lead and for the same time of the month. So this is one example which I've just found on the web. Is a very simple case. The people who wrote this article, they wanted to correct the systematic error in the Niño 3.4 index, which I'm sure most of you are familiar with, but it's basically the anomaly of sea surface temperature in a box along the equator that covers the central and eastern Pacific Ocean. So what they did is that they computed a distribution from an observational source, which is here the OISST from NOAA. Then they looked at the ECMWF forecast for the same quantity, and they computed the probability density function, which is the one in red, while the OISST is in blue if you look at the left corner. And basically what they wanted to do is to simply correct the forecast in such a way that at least the mean of the forecast, of the corrected forecast, was the same as the mean of the observation. So what they did is that they just applied a very simple shift. You can see it in the diagram on the right. Basically, they just moved the red distribution by changing the mean and aligning the mean of the forecast with the mean of the observation. So basically means going from the red curve in the right diagram to the dash black curve. And you will see that the mean of this distribution now coincides with the mean of the blue one. So this is the simplest way of correcting. You just correct the mean. And that is based on the assumption that the model systematic error at a certain forecast time is a constant bias. So that it doesn't change, for example, in different years. So if this is true, then the model anomalies, so the deviations from the model mean, are a proper estimate of the real world anomalies. So in this case, if you're interested, for example, in monthly values, you don't have to run any program, as the previous Edu and Chris discussed. You can just go to the C3S website and download the anomalies produced, multi-mean anomalies produced by the individual models. And so this automatically provides this simple bias correction. However, you may be faced with different situations when not only the mean of the distribution is different, but also the shape. You may have a different standard deviation, you may have a different skewness. So one distribution may be more or less asymmetric than the other. That is often the case for hydrological variables, typically precipitation, where the distribution is not really Gaussian. So again, here we have an hypothetical example. On the left, we have the observations, the probability density function for the observation, which is the black line. We have a model distribution, which is quite different, which is in blue, still on the right. And what we want to do now is not only to correct the mean, but really to correct the whole distribution in such a way that it fits as much as possible to the observed probability density function. And this is done with this technique that is called quantile mapping. The version which I describe is often referred to as empirical quantile mapping because it's really just based on the raw data. So from the probability density function, if you actually integrate it, so you don't want just to know the probability density at one point, but just the probability that you will find the value less than a certain threshold, then you move to what is called the cumulative distribution, or simply the distribution, which is the graph on the right-hand side. And okay, this is not an exact correspondence to the graph on the left, but just to illustrate. So you will have an observed distribution, which is again the black line. You will have an uncorrected model distribution, which is the blue line. And what the quintile mapping does is that we assume that the correct calibrated value corresponding to one forecast value is the one that has the same value of the cumulative distribution. And we call these values quantiles because usually basically it tells you what percentage of data is in a certain range of values. So suppose you have your observational data set, then you have your, which is the black line, then you take all the reforecast that cover the same period for which you have observed data. You put them all together, all the years, all the ensemble members, and you will get the blue distribution. Now, suppose now you have an operational forecast. This will give you one value, which corresponds to one of the gray arrows. And so you go up from the original value up to a point on the blue curve. So what you want to find is, I have this forecast value, I now compare it with the distribution of the reforecast. And so I want to know what is the value of the distribution that corresponds to this value. So this would be the quantile. And then basically, as I assume that the correct temperature is equal to the observed temperature, which has the same quantile of the distribution of functions. This corresponds to the red curve. So you can see that in one case, this correction will give you a negative correction. So you will turn your original value into a lower value. And in another case, because of the different shape of the distribution, you will turn it into a larger value. These pictures are taken from two reports. I may suggest they are easily found on the web by if you type quantile mapping in Google. And for example, the Metro Swiss report gives a detailed description of an application of quantile mapping for Switzerland. Now let's make a simple example with just a few data so that we can actually fit the data on the screen. So suppose we want to correct again the distribution of the Niño 3.4 SST anomaly average for December, January, and February. So this particular data have been downloaded from the NOAA website. So the original data are multi-values, so I averaged December, January, and February values for each year from 93 to 2017. These are 25 years that correspond almost to the calibration period for the C3S models that you find. You will understand why I added 2017. You see, and so, okay, so for each year, you have one value, which is the anomaly. So the difference of sea surface temperature in the Niño 3.4 box, so along the equator in the central and eastern Pacific, with respect to the climatology, which is in this case an average for the period 1981 to 2010. Now, if you go to C3S website, you may find a different, now in many sites, people use a more recent climatology for 91 to 2020, but in this case, the data were compared to this climatology. It doesn't really matter for our purpose. Okay, you can plot the data, you will see the time series, so you will recognize the very large value in winter 97-98 and 2015-16, and other less extreme El Nino values, which, for example, the one in 2010, while, for example, in 99, 2000, 2008, 2011, we had La Nina events. Okay, so this is just a simple time series. Now, what we can do is that we have all these values. So the two columns on the left are the same as in the previous plot, but now you can sort them. So you can order them from the lowest to the highest value. So we find the lowest value is minus 1.7 and the largest value is about 2.4. Now, you can ask yourself, once you have sorted these values, how many of these values are actually less than the value you are looking at? So, of course, if you look at the first one, minus 1.7, there are no other values which are lower. So the probability in percentage of finding a value which is lower than that is 0. You go to the second value, and you will have one value, which is less. And since we have 25 years, that corresponds to 4% of the data. So in the last of these columns, you will see 4. And then you go on. And of course, when you come to the largest value, 2.41, then basically, apart from the value itself, all of the other ones will be lower than that. And so the proportion of values which are lower will be 96%. Okay, now we have this, you have this data in the third column and in the fourth column. And what you can do is that you plot one against the other. And you get the value, the graph at the bottom. And that is the cumulative distribution of the seasonal mean of the Niño 3.4 values for these 25 years. Now, does it look like those nice, more smooth curves which I showed you before? No. Because we have only used 25 values. And therefore, the distribution, if you compute these distributions for a very limited number of data, then you get something which is very noisy. So we could use quantile mapping in theory on the seasonal means, but we will get something which is very noisy because there are wide gaps between the values in individual years, so the functions are not very smooth. Now, what can we do if we want to apply this technique to other fields? Because actually I chose this example because it was easy to find the data, but as we have seen in one of the previous slides, for the Niño 3.4, maybe a simple shift in the mean would be enough, and it would be just good enough to get the multi-mean data from the C3S website. I suppose you want to do it, for example, for rainfall in a specific region. Then content mapping will work much better if you use daily data. And this is basically what we have done for this project. So this is basically the steps that we have followed. So first of all, you have to select an observational data set which includes daily data, either from stations or on a high resolution grid. And for example, for soil temperature, you could use ERA-LAND. For precipitation, you could use CHIRPS, which is quite frequently used nowadays. That's pretty high resolution. So this will be your observational data sets. It will cover a certain period, and you can create a cumulative distribution for each of the observation points that you are considering. Then you can go to the C3S website, and you can extract the reforecast data for the same period covered by the observations. And you first have to interpolate to the observation points, because you want to do your downscaling on the higher resolution grid or on station values. One word of mention, linear interpolation always produces smoothing. So it's better to do this before at this stage, because then you hope that the quantile mapping will also correct the additional error that is introduced by the interpolation. So then for each month of the year, you compute the distribution of observed values and reforecast data at each point, and the correspondence between the two distributions will define the quantile mapping. So for the reforecast, this needs to be done for each forecast month separately because of the climate drift in the forecast. We have said at different lead times in the forecast, the climate of the model changes because we start from the observed data, so from the real climatology, and the model gradually drifts towards its own climatology. So if you take, for example, the forecast for if you want to do a downscaling for June, from, for example, a forecast started in April, then you have to aggregate all the month 3 forecast, month 3 reforecast for all the available yields. Okay, so now you've done this, so you are ready to do your application to operational seasonal forecast. So again, you extract daily data on the available grid that for the seasonal forecast on C3S will be a 1 degree grid. You interpolate this data to the observation point. And then for each observation point and each day in the forecast month, you can find the closest daily value in the reforecast archive. Then you have the distribution of the reforecast and you can find the corresponding quantile. So let's say that one value corresponds to the 65th percentile. Then the calibrated forecast will be the observed daily value with the same quantile on the closest quantile if you cannot find exactly. Okay, so you will end up with a large set of daily calibrated values, and then you can actually aggregate them back into monthly means, or you can use the sequence of daily values, corrected daily values, to compute some intra-seasonal statistics, for example, the proportion of dry days, or for example, temperature with maximum daily temperature exceeding a certain threshold. So we did this exercise, and to do that, we did it for maximum temperature, minimum temperature, and precipitation. So the web address at the bottom is basically the entry in the CDS archive where you will find this single level daily data from seasonal forecasts. Okay, so I mentioned that we did this exercise in the context of a project. The project is called Albatros. It's coordinated by University of Bologna in Italy. There are a number of partners from Europe, from Africa, and from international organizations, for example, UNESCO or NGOs like Oxfam. And the goal of this is to produce climate services or nature-based solutions for climate change adaptation. So we will actually focus on the climate services for seasonal forecast. And so we have basically applied the technique which I have described before. So basically we've done quantile mapping, statistical downscaling of ECMWF seasonal forecast. And as an example, as a sort of starting point, we have calibrated the data using ERA 5 or ERA 5 land data. I say, so ERA 5 land has been used for temperature data, maximum minimum temperature. Actually, you can get precipitation from ERA 5 land, but these are actually a forcing for the land model. So they are simply data from precipitation from ERA 5, which are interpolated to the higher resolution grid of ERA 5 land. So we take daily maximum temperature, minimum temperature, and total precipitation accumulated into one day to compute this monthly distribution. So from the forecast on the C3S archive, you get this forecast on a 1 degree grid of the order, so the resolution is of the order of 100 kilometers. The resolution of the ERA 5 land grid is of the order of 10 kilometers. So we get the analysis for 30 years from 1993 to 2022 on the ERA 5 land grid. We get the reforecast from the ECMWF system at 6 time lags. When it's downloaded from the C3S website, you get the data on a 1 degree lat long grid. And in the reforecast, you have 25 ensemble members. Now, because ECMWF has not actually changed its model in the years after 2016, which is the nominal end of reforecast, we could actually extend this period by taking the first 25 members also of operation on the forecast and therefore to cover a full 30-year period. We did that because in the next generation of the system that will be available on C3S, the actual reforecast period will be extended to 2022. So again, we take Tmax, Tmin, and 1 day precipitation. And then we get the operational seasonal forecast for 6 months, 51 ensemble member. And we apply the quantile technique to correct the data for daily values. And then what we do is that we compute some products. So first of all, we can average all this data and compute multi-means and multi-mean anomalies. These are some examples of maps. So an important thing is that we do that for each individual ensemble member, so that we go from an ensemble of non-calibrated data, of original data, to an ensemble of calibrated data. So then we can compute some statistics. For example, here you see on the left column in the plots the median seasonal forecast for maximum temperature at the top, minimum temperature in the center, and precipitation. And on the right-hand side, you see the difference with respect to the observation climatology. For precipitation, it's not actually a difference, it's a ratio. That's why you see some very black areas, because it's simply, if you have zero precipitation, that of course will be, will go at very large negative values. You can compare that with what you directly find on the C3S website for these particular months. And in this case, I've chosen the area that covers Africa and the Western Indian Ocean. And what you can see is that if you compare the ECMWF maps with the downscale maps, you, of course, by definition, you will see more details. Now, one question is, will this improve your forecast? Now, the answer is it will only improve your forecast if the original signal has skill. So this is not a panacea. It has to be reminded. So many people, when you ask, what do you need? What would you like to have from seasonal forecast? In many cases, users in tropical countries say, oh, we would like to have more spatial detail because what we see in the maps on C3S is too smooth. Well, we can understand that, and so this is the tool to do that, but you have to remember that we cannot really create seasonal skill by this. So if there is skill, then this technique will give you an additional spatial detail. For example, for temperature, if you want to know the absolute value of temperature, that will take better care of the differences in topography, for example. But if the original signal has no skill, then okay, there will be also no skill in your downscale forecast. So this has to be taken in mind. Okay, this is another example. So the previous one was for just with the 1 month lead time. This is with a 3 month lead time. And again, if you compare the maps of the anomalies, so in the right-hand column with the maps from ECMWF, you can see that the features are roughly corresponding. You see much more detail For example, if you look over South Africa, you can actually see some differences between areas where the downscale signal is dry and where it's wet. You don't see it very much in the ECMWF forecast, but again, downscaling that does not necessarily mean that you are increasing the skill, so you have to verify whether the downscale product is actually useful. Now, I said another advantage, which I think is quite important in downscaling daily data and then aggregating, is that you can also create products about the statistics of daily value. So what we do is that we also produce box plots to describe the evolution of the variables. And okay, if you look at the ones on the left column, these are for maximum and minimum temperature. So this will give you the range of the monthly means in the 51-member ensemble compared to the observed climatology, and you will have the median. The box is basically the range between the 25th and the 75th percentile, and the instead the bars go from 10 to 90. Okay, these are just box plots for the mean values, but if you now go to the bottom right, what you will see are other indices which are actually derived from daily values. And let me just zoom out so you will see it better. Again, let's focus on the plot on the bottom right. So what you see here is the length of the longest dry spell. So if you want to know for how many days you will have no rain, then again, this is something that you can compute from these calibrated daily values. So for example, this was a forecast starting in February. So in the first month, the forecast basically had a range between 11 and, if you look at the range between 25th and 75th percentile, this actually tells you that that corresponds to a range between about 11 and 20 days with a median of 16 days. You may want to have statistics about the extremes, or simply about the rainy days. What is the proportion of rainy days when you have more than 1 millimeter per day, or the proportion of rainy days when you go beyond one threshold, which in this case has been chosen as 10 millimeters per day. And again, you can create box plot by looking at the distribution of this particular value within the various ensemble members. Okay, this is a simple application. As I said, this is a sort of demonstration. So far, the Albatros project is still evolving, so this will not be the final value. Probably we will move to CHIRPS data or one of the latest GPCP data set for precipitation. But this was just basically to show you an example where you can get data from the C3S website and you can use them to do a nonlinear bias correction and a statistical downscaling at the same time. Okay, so take-home messages. So don't simply rely on graphical products, especially those for seasonal treatment means, as has been shown in the previous demonstrations. You have plenty of data on the C3S website that will allow you to create products which are tailored to your specific needs. So downloading multi-mean analysis is the simplest way of getting bias-corrected data, but processing daily data may provide a better calibration, especially for hydrological variables, which have a non-symmetric distribution. So the bias is usually not simply a shift. Another important thing is that we have talked about an observational data set. So we have, in this case, we have used ERA 5 or ERA 5 length. Now, any observational data set have errors. This is important. So if you want to calibrate your forecast against an observational data set, you first have to be sure that you can trust this observational data set in your area for the variable you are interested in. So you can do that by, for example, checking the consistency in the variability among different data sets, or if you have station data, you can actually compare the values with station data. So if you are calibrating against an observational data set that has a poor correlation with your actual observed data, then of course you will not add any useful information. Now, many people, I've seen many studies where people have used the rainfall data from reanalysis. Remember that rainfall data from reanalysis come from model parametrizations and not from rainfall observations. I've seen a paper that where they think that the ERA 5 precipitation come from satellite data. That's not true. So they are produced by the model parameterization in very short range forecasts, essentially. So satellite only or products where satellite and rain gauge data are merged may be more reliable than reanalysis in some tropical regions. Usually this is, as from my experience, this is more so in dry regions. Usually in areas where it rains a lot, reanalysis are pretty good. It may also depend on the region. You know, we have done within C3S verifications of monsoon rainfall. It turned out that ERA 5 was a pretty good match to GPCP over India, but not very much over China, for example. And we have no time to go into this detail for that, but you have to make this comparison between different data sets to find out what observational data set will be useful for you. Remember that linear interpolation introduces spatial smoothing, so if possible, avoid interpolating data which have already been interpolated. So, for example, if you take rainfall data, you can directly take them from ERA 5 and then you interpolate to the points where you want to have your signal, rather than taking them from ERA 5 land where they are already been interpolated. And again, I say again what I said earlier, statistical calibration and downscale only improves forecast information if the large scale forecast is skilled. So as Eduardo showed, you can find maps of skill. You have tools to compute the skill of these models in your area. You don't necessarily need to take all the models available in the C3S website. You may find that some of them are perhaps more skillful in your area than others. So assess the skill of the original model forecast as a preliminary step. And that is all I have to do. And thanks for your attention.
Great. Thank you so much, Franco. That was very interesting, comprehensive presentation. Lots of good insights. I don't see any questions in the chat. There's a question from Anka, actually.
Okay. Shall I stop sharing?
I think you can stop sharing. Yeah. So does anyone? I see Faka, you have your hand up.
Yes, thank you. Thank you, Chris. Yeah. We thank our colleague from the Italian Meteorological Department for providing this tool for African people. Here, I would like just to ask if the software is available for other African countries who did not participate in your project to use the tool, and if there could be also a way where a more organized training on the user need or user manual for the tool to be provided so that we can make a large use of your methodology. Thank you.
Franco, your microphone is muted.
Yes, if you could
sorry,
unmute.
yeah. I had to reconnect because somehow there was an interruption. So there will be soon, so at the end of summer, a deliverable for this project where this preliminary phase of the tools developed for the project will be described, so there will be an information there. But I want to stress that this is a very common technique. So if you just go to Google and you type quantile mapping, you will get references to a lot of publications already that explain how you do this, you can do this technique. So basically what you have to do is simply to create these distributions and basically create a correspondence between one and the other. So the application at the moment has been coded by my colleague, Daniel Pavone in Python. At the end of the project, there will be really a software tool that will be delivered to all the participants. But this will have to be refined as a function of the needs of the user. As I explained in this Albatros project, there are a number of what we call hubs in sub-Saharan Africa. They are interested in different variables. And so the tools will be somehow finalized for those hubs who want to apply this technique. But I don't think you have to wait for that. I'm sure you will find on the web a lot of applications of the quantile techniques. I don't know if there are already things like Jupyter notebooks that already do that. I'm sure there is already Python code around to do that. At the moment, as I say, we are developing this, so it's basically a beta stage. So it will be made public, but let's say not immediately.
Okay, thanks, Franco. I'm not sure if that answers your question. I can see a hands, a thumbs up, so I take that as a good sign. There was a question from Anka. I don't know, Anka. Do you want to raise that question?
Yes,
already?
I can.
Yeah, great.
I can. So, Franco, I was looking at the difference between your maps and ours for Africa, and it was interesting to see them. I wondered if you took into account the fact that much of the white on our maps is to do with the fact we apply significance testing. So if we were to color all the anomalies that we did compute in, we'll get a lot more color there without any downscaling or anything. More generally, though, I'm curious if Albatros is looking into significance testing and error bars, because we know that many producers don't do this. And we know that some users would benefit from having an idea as to whether those small anomalies are actually something that needs to be taken seriously, or it could be a thing by chance, as well as talking about uncertainties and error bars on skill estimates, because some people will make a choice of a particular, say, configuration of multi-model in comparison to another, simply based on things that aren't significantly different. So I wondered if you want to comment on this a little bit, or if you just tell us Albatros is doing it, we can wait for it.
So basically, what I've shown here is basically a demonstration that we have shown to the different hubs, so the different participants in sub-Saharan Africa. So what we have actually asked these hubs is to provide local data, because as you said, you have to verify whether this smaller scale information is actually useful to them. So whether this tool will be, I don't expect that it will be useful everywhere. Probably, as I say, if you have regions where there are very strong elevation differences, complex topography, okay, the correction in temperature will be useful, although maybe that can be achieved with much simpler ways than quantile mapping. Quantile mapping is supposed to work better or to be more useful for precipitation. So what we are encouraging now the African participants is actually to send us real data from the locations, from the regions where they would like to have these climate services delivered, so that we can actually verify whether this downscaling and content mapping is actually improving the information which is available. So you're absolutely right. So you cannot just take every detail in those mesh for granted. And another exercise that is being done as a part of the project is, in fact, it was basic one, to assess the skill of the regional forecast in different regions. So, for example, now it has been decided that we will focus on 3 different parts of Africa, so West Africa, East Africa, and South Africa, in possibly different seasons, in order to exploit some teleconnections that the model usually get reasonably well. So we don't expect the technique to work uniformly across the year. It will only work if there is skill in the large scale signal that we know is usually restricted to certain periods of the year when you have a more clear influence of, for example, the ocean conditions.
Okay. Does that answer your question, Anka? Great. I see that Faka, you have your hand up.
Yeah, just a follow-up on the last comment from Franco. Is there any technical reason to you avoiding the Central Africa by concentrating only Western, Eastern, and Southern part?
Well, we are not totally neglecting in the sense that some products will be tested on the whole of Sub-Saharan Africa. When I talk about East Africa or West Africa, it's not really only the coast, but basically, we know there are phenomena for which we have good predictive skill in the seasonal forecast, and that's the West African monsoon, the short rain for East Africa, and usually we get reasonably well the impact of El Nino in Southern Africa. Now, for each of these phenomena, there are sort of extension if you look at the areas where there is skill. So sometimes the central part of Africa is connected to one of these regions, and in other parts, in other seasons, is connected to a different part. So as I said, we are trying to concentrate on the areas where we know that there is skill in the forecasts, because otherwise but it's not that we are neglecting Central Africa, it's simply that for Central Africa, it's a bit more tricky to define periods of teleconnections that always work. And so depending on the season, Central Africa may be connected to one of these other 3 regions or influenced by different kind of teleconnection. So the other reason is simply the participants to these particular projects are distributed in these 3 areas, and to Madagascar in addition. So basically, the participants are in one of these 3 areas that I've mentioned. But in principle, we can apply the technique everywhere, provided we have some local data to validate the downscaling.
Anka?
Very briefly, Franco reminded me of something. There is a difference between things developed in a research project and things developed and deployed as part of a service. The research project has partners that have particular interests, and the research project has a finite lifetime. So I think ideally one ought to look about tools like these being implemented into services where they will be maintained for people to use longer term.
Thanks, Anka. Just want to also point out a couple of comments in the chat. So Chris Goddard sent a link to the documentation of the IBICUS package, and quantile mapping is actually built into to IBICUS. So we also have a link to IBICUS in our Jupyter notebook tutorials, but there's also the link is posted in the chat as well. And indeed, there are some examples in the documentation with C3S data, not with seasonal predictions though, but with projections. But nonetheless, there are some Jupyter notebook-based examples there on how you can do bias correction, and I believe also the quantile mapping technique using IBICUS. So I'd see if there are any other questions. I don't see any other hands up, and I don't see any other questions in the chat. So I think we could maybe break for lunch at this point. We have about almost a bit more than 45 minutes, and then we can come back at 1 o'clock CEST. When Chris Goddard will then present the seasonal forecast verification practical, and we'll also hear from JRC on the ClimSA station. So thanks a lot for the great presentations, and thanks for everyone for watching, and we'll be back here at 1 o'clock CEST.